Namaste and welcome to the lectures on mathematical foundations for machine learning. We are in the ninth week, and in the last lecture we looked at the idea of gradients and directional derivatives. We saw how the gradient points to the direction of steepest ascent, and along the level curves how the gradient was 0. We saw all that. In this lecture we are going to look at the chain rule for the partial derivatives, and we will also look at the idea of Jacobian and Hessian. This Hessian matrix keeps coming in machine learning. When you look at the second derivatives and you want to minimize a function, you actually get to the Hessian and check certain properties of Hessian matrix, and then say that look, this is what it is, right, meaning okay, the function basically is concaving up and so on, right. So let's quickly get into the idea of the rules for partial derivatives, partial differentiation, and then the chain rule, and then Jacobian and so on. So let's look at this. Rules for partial differentiation. Rules for partial differentiation. I mean, again we are going to consider a function which is going to map, let us say, Rn to R. I mean, if you find it difficult to understand this Rn to R, you can actually do it with respect to R2 and then say R2 to R, R3 to R, and then understand this. So suppose I am going to look at this. There are two functions. Let us say let f of x and g of x be two functions. Of course, continuity must be there, then you should have derivatives to be there, it can be differentiated at a particular point. So you have that, or the derivatives be available at that particular point. So I am going to take f of x vector, that means this is going to be a function of n variables, this is going to be a function of n variables. So f and g are there. So I am going to look at what is the partial derivative of this function, the sum of f of x plus f of x and g of x, right. So what does this mean? You basically collect all the derivatives of the partial derivative of the function f and collect the partial derivatives of the function g, and you want to find out the partial derivative of the sum of the functions f and g, where both g and f are functions of multiple variables, say n variables here x1 to xn. So this is nothing but dou f of x bar, that means you take the partial derivatives of the function f, add it with the partial derivatives of the function g. This obeys exactly the differentiation rule for addition of functions. The derivative of sum of function is nothing but sum of derivatives, that is exactly what we see here even with partial derivatives. Then I want to look at the second property, which is basically the multiplicative property. I want to look at dou by dou x of, let us say, the product of two functions of multiple variables f into g, right, is nothing but exactly like what we had there. We are going to say dou f of x by dou x vector into g of x plus f of x into dou g of x, the partial derivative of x, I mean g with respect to x. So this is what we have. One of the most important results that we would often come back here again, as I keep saying, even in the previous lectures I've told that the idea of chain rule of differentiation is extensively used in neural network and BAP propagation algorithm. So, we want to look at chain rule with respect to partial derivatives. So, I am going to look at chain rule with respect to partial derivatives. So, I am going to have the derivative of a composition which is given by f dot g, right. This indicates it is a composition. That is nothing but f of g of x. So, I am going to get dou by dou x of f, this is nothing but f of, right. So, this is nothing but dou f by dou g into dou g by dou x vector. This is what we have. We will just take a couple of examples to understand this, and then let us get going with the other ideas that we were waiting for doing in this lecture. So, let us just take a simple example here. Let f be a function which is going to map R2 to R. That means, let x1 and x2 be the variables, x1, x2 be the variables. The variables with on which the function f depends, and let us say x1 and x2 in turn depend on t, be functions of another variable t, be functions of variable, let us say t. So, what is df by dt? df by dt is the function, the variation of the function with respect to t. This is nothing but dou f by dou x1 into dou x1 by dou t plus dou f by dou x2 into dou x2 by dou t, right. Dou f1, dou f by dou x1 into dou x1 by dou t plus dou f by dou x2 into dou x2 by dou t. This also looks like something interesting which you have seen before. This is of the form u1 v1 plus u2 v2, which is nothing but the dot product of this vector u1 u2 with v1 v2, right. That is exactly how this looks like. So, we are going to express this as df by dt is equal to, collect the partial derivative of the function f with respect to x1 and x2, basically you got your gradient here, into dou x1 by dou t and dou x2 by dou t. So, we basically brought this as a matrix product now, right. We got it as a dot product of two vectors and we have this. Let us take an example here and get it, like example. Let me take this f of x1 comma x2 is equal to x1 cube plus 2 x2 squared, and let us take x1 to be equal to t and x2 to be equal to t cube plus 3t square. Right. So, let us figure out what is this dou f by dou x1 by dou t, then dou f by dou x2 and dou x2 by dou t and so on. So, we will understand this. So, we use this. So, what is dou f by dou x1? The partial derivative of the function f with respect to x1 is nothing but 3x1 squared, and dou f by dou x2 is nothing but 4x2. And dou x1 by dou t is 1, dou x2 by dou t is basically 3t square plus 60. right. So, what do we have? We just apply this rule here, we write this as df by dt is nothing but dou f by dou x1 dou f by dou x2 into dx1 by dt dx2 by dt, which is nothing but we have 3x1 squared 4x2 into 2 okay, I just took it as t, okay fine. So, this is going to be into 1 and this is going to be 3t squared plus 60, right. So, we have this which is nothing but what is x1 squared? X1 is equal to t. So, I have 3 into t squared, right, plus I have 4 x2, x2 is nothing but let me write this as okay 3 x1 squared, let me write this first, this is 3 x1 squared plus 4 x2 into 3t squared plus 60. x1 is t, so I am going to take it as 3t squared plus 4 into t cube plus 3t squared into 3t squared plus 60. You can simplify and get the value of df by dt. So, this is how the chain rule operates. In the case like we have a function of multiple variables, then we are going to have a something different. Say for example, if we have, so this example is over here, suppose if let us say f of x1 x2 we have and function of x1 and x2 and x1 is a function of let us say some g1 of s comma t and 2 variables and x2 is another function which is g2 of s comma t. Then how do we apply chain rule? So, we are going to look at the chain rule which is nothing but dou let us say dou f by dou s, dou f by dou s is nothing but dou f by dou x1 into dou x1 by dou s plus dou f by dou x2 into dou x2 by dou s. Similarly, we have dou f by dou t, I will take it as g1 okay, yeah that is fine. So, I am going to take dou f by dou t which is nothing but dou f by dou x1 into dou x1 by dou t plus dou f by dou x2 into dou x2 by dou t. Oh, this is something again interesting, like how does this look like? So, how does this look like? So, I am going to take this df by d of s comma t is nothing but dou f by dou x vector into dou x vector divided by dou of s comma t, which is nothing but I am going to pull that gradient out. This is of the form, if you look at this, this is going to look like a1 x1 plus a2 x2 b1 x1 plus b2 x2, oh which is again a matrix form. So, I am going to write this as the gradient which is nothing but dou f by dou x1 dou f by dou x2 into this matrix. What is that matrix I am going to get? Dou x1 by dou s, dou x2 by dou s, oh sorry, dou x1 by dou t, dou x1 by dou t, then I am going to have dou x2 by dou s and dou x2 by dou t. So, I get a matrix product here. So, this is basically the chain rule which is basically expressed as a matrix multiplication, right. Great. So, this is chain, you can work out some problems on this, this would I mean you would get some insights into this, right. Now, where are we headed to? we are getting into a very interesting topic here now, which is basically a function. Let us say I have, till now what we studied, we said that y is equal to f of x, where the function was basically mapping r to r, single variable to another variable y. Then I said we went to this multiple variables where I have f of x comma y. Therefore, this function is basically going to map from r2 to r. Now what I am going to do is I am going to do something interesting. What is that? What happens if my function takes n variables and outputs m values, right? So what are we going to do? We are going to look at this. So I am going to look at a simple case where we have a function. Let us say I have this, let us say b1 is equal to, let us say f1 of x1 to xn, b2 is equal to f2 of x1 to xn, and so on. bm is equal to fm of x1 to xn, right. Now what does that actually mean? This simply means we are going to have a vector valued function here. So you are going to get a vector here, and that is going to be a collection of functions which are themselves what would you call multivariate functions. This is what we have. Have we seen something like this before, where we have b1, b2, bm, f1 of x1 to xn? Of course we have seen this before. Where is that? We have seen b1 is equal to, let us say a11 x1 plus a12 x2. We have done this before, a1n xn. Go on, we have bm is equal to am1. That is basically capturing y is ax is equal to b, am1 x1 plus am2 x2 plus etc plus amn xn. So what is this going to do? This function is going to map Rn to Rm. What is that? A function which maps Rn to Rm. We did in the second week of this course. That is basically a linear transformation, right. We looked at linear transformations. Right, we looked at linear transformations. That means here is a function f which is going to map from Rn to Rm. That means each of these that you have is a function of n variables. Now therefore each of these function is going to vary in n different directions, and therefore I am going to look at the gradients of each of those functions f1 to fm. And where do I put that? How do I populate this guy? What kind of a structure I am going to have? And that is what we are going to look at. So we are going to enter into this one. So what we are going to do is we are going to look at a function which is basically where the input is a vector and the output is a vector, right. So we have a vector valued function and the output is also going to be a vector, right. So we are going to look at this. So how are we going to put the gradient of all these things together? So what I am going to do is we are just going to take this, we are going to say df by dx vector, df1 by dx vector, df2 by dx vector, and etc. dfm by dx vector. That means the gradient of each of these functions I am going to look. Oh well, I know how to create this gradient vector for a single function. What did I do? We just took this. Every row is basically going to be a gradient. So I am going to take this as dou f1 by dou x1, dou f1 by dou x2, etc. dou f1 divided by dou xn. Similarly, I am going to have dou f2 by dou x1, dou f2 by dou x2, etc. dou 2 by dou x n, and so on. We get dou f m by dou x 1, dou f m divided by dou x 2, etc., dou f m by dou x n. So, this is what we have. So, what have we done? This is basically collection of the gradients. So, what did we do? We basically took the gradient of the first function, and then we had the gradient of the second function, and so on. We have the gradient of the mth function, right. This is what we have, right. And there is a name for this matrix that we have, which is the collection of all gradients. If you have a vector valued function, that means you take input vector and then give an output vector, then the corresponding gradients would be a matrix of size, say, m by n, m rows and columns, and this you call this as your Jacobian matrix. You call this as your Jacobian matrix, right. Okay, great. So, all just you need to do is just stack the gradients and you get this, right. Okay, good. Let us take a simple example here. Let us take a simple example and compute the Jacobian. So, what is the example you are going to look at? I am going to take this is to indicate that the function f itself is a vector valued function of it takes inputs. Let us take this to be, let us say, x 1 x 2, and let us say this is going to be x 3, let us say x 3 squared, x 1 x 2 and x 3 squared. So, I want to get the gradient. So, this is going to be what? The function is going to be like this, f of x 1 comma x 2 comma x 3 is basically x 1. So, basically this maps, what does this map? This basically maps R 3 to R 2. This maps R 3 to R 2. So, what are we going to do? So, I am going to take, so we have x 1 x 2 and we have x 3 squared. Right, this is the function that we have. So, let me take, so this is going to be my f 1 of x 1 x 2 x 3, and this is going to be f 2 of x 1 x 2 x 3 is what I have. So, I want to look at dou f 1 by dou x 1, which is nothing but x 2, dou f 1 by dou x 2, which is nothing but x 1, and dou f 1 by dou x 3, which is 0. Similarly, dou f 2 by dou x 1, which is x 1, dou f 2 by dou x 2, no, this is going to be dou f 2, this is going to be 0, dou f 2 by dou x 1 is 0, dou f 2 by dou x 2 is 0, and dou f 2 by dou x 3 is going to be 2 x 3. Therefore, the Jacobian is going to be like this, it is going to be x 2 x 1 0 0 0 2 x 3, right. We see that this is 2 by 3, and this was basically one function, this is one function, and that is of 3 variables. So, this is going to be the Jacobian that you have, right. Great. Now, what we are going to do is, fine, we have looked at a function of single variable, I mean a function of single variable, function which maps multiple variable to a real numbers, and that is where we got into the idea of gradients. Now, we look at a function, we are going to capture a vector valued function, that means the output is going to be a vector and the input to such functions are also vectors. So, then we got into the idea of gradients by stacking up all the gradients in a matrix form of say dimension m by n, you call that as the Jacobian matrix. Now, there are two things that we can that we need to look at here as far as the Jacobian matrix is concerned, or the what would you call the matrix in which you are going to put the gradients. There are two things that we can do. One thing is, we have in all these cases we have put the gradient as a row vector. You remember when we did gradient, we also spoke about this. The gradient is a row vector here. You could actually put gradient as a column vector too, in which case the dimension of the Jacobian matrix will change. If you take the gradient to be a column vector, the Jacobian would become n by m matrix. In case you take the gradient as a row vector, the Jacobian will basically become m by n matrix. So, let us write that. If gradient is a row vector, then Jacobian will be of dimension m by n. If gradient of the function, I will take this as f vector itself. So, this is going to be gradient of this f vector is column vector, then Jacobian will be of dimension n by m, right. We have this m by n and n by m. So, we have a name for these two guys. What is the name for these two guys? Whenever you have the what would you call, whenever you have your layout wherein which you have the gradient to be stacked in the form of the row vector, the gradients are all row vectors, then you call it by some name where the this is the case where I have m by n, then that I am going to call it as the numerator layout. This is called the numerator layout. And if it is going to be the other case where it is treated as a column vector, then you call it as the denominator layout. Right. So, you have the numerator layout and you have the denominator layout. Of course, once you choose like what is the layout that you want, then stick on to it, be consistent, and then start working on it, right. So, that is what is basically the numerator layout and basically the denominator layout is. Okay. So, how do we look at it? I will just make a what do you call a differentiation between these two guys. So, I will say numerator layout and denominator layout. Right, numerator layout is going to look like this, where it is basically for a vector valued functions. You have the function outputting a vector and the input is also a vector. So, I am going to have this. This is going to be dou f1 by dou x1, dou f1 by dou x2. Now, basically we understand this. So, this is something which we have done, dou f1 by dou xn, and the second one is dou f2 by dou x1, dou f2. Basically, the rows correspond to the gradient. So, you have this etc. dou f2 by dou xn, then etc. dou fm by dou x1, dou fm by dou x2, etc. dou fm by dou xn. I mean, where will we use all these things? We will come to it in the next module. When we do, we will look at when we try to do matrix derivatives and so on, we will be using this, and that will form the crux of your next module, next week's module. So, this is basically your numerator layout, and let us look at the denominator layout. The denominator layout is going to look like this: dou f by this vector divided by dou x vector is equal to. Now, what am I going to do here? I am going to take the gradient transpose of the gradient. When I use gradient as the row vector, now I am going to do the transpose of that. So, I am going to write this as dou f1 by dou x1, dou f1 by dou x2, etc., dou f1 divided by dou xn. The second column is the gradient of the second function, dou f2 by dou x2, etc., dou f2 divided by dou xn, and it goes on. So, you have dou fm, the mth column is going to be dou fm by dou x1, etc., you have dou fm by dou xn. Now, you can very clearly see the difference. This is going to be a matrix of m rows and n columns. This is going to be a matrix of n rows and m columns. Please note the difference here, and that tells you like how you are stacking up your gradients, right. So, that is what we call as your numerator layout and denominator layout, right. Okay. As I said, like once you use this, once you fix the layout, you start being consistent with that, don't change, don't mix, and it is going to be a problem if you are going to mix. The next thing that we are going to look at is quickly we will have a look at the matrix of second derivatives. Till now what we have seen is just matrix of the first derivative. Let us look at the matrix of second derivatives. Okay. So, what are we going to do here? Okay, let us look at this. Say suppose I have a function which is nothing but f of x comma y is equal to x cube y square plus x squared y cube. I have x cube y squared plus say x squared y cube. Now, let us look at what is dou f by dou x. Dou f by dou x is nothing but 3x squared y squared plus 2xy cube, and dou f by dou y is nothing but 2x cube y plus 3x squared y squared, right. This is what we have. Now, what do we see here? Something interesting happens here. What is that? The derivative of this function f is itself a function of x and y. Derivative, the partial derivative of f with respect to y is itself a function of x and y. And remember, when we looked at the second derivative, as in the case of single variable function, we said the second derivative is going to give the rate of change, the acceleration here. Similarly, we will do the same thing here, but there is a small problem here. What is that? This rate of change that you look at, the rate of change that you look at here is itself a function of x comma y. This itself is a function of x comma y. Therefore, I can nudge again along x axis and I can nudge along again along the y axis and so on. Therefore, what we see is we are going to have dou by dou x of dou f by dou x, and we have dou by dou y of dou f by dou y, which makes sense. But we see this dou f by dou x is also varying with respect to y. So, what I will do is I will take the other partial derivative, which is dou by dou y of dou f by dou x, and I will take dou by dou x of dou f by dou y. So, what do we get basically? For a single function of two variables, we have two elements in the gradient, but the second partial derivatives you have four terms of them, which are basically the dou square f by dou x squared, dou square f by dou y squared, we have this, and here we have dou square f by dou y dou x and dou square f by dou x dou y. So, what do we see here? We see that the second partial derivative for just two terms, a function of two variables, is basically giving us four second partial derivatives. Four partial derivatives implies, like, I mean, you are going to look at the cross, these are basically the direct second order derivatives, and these are going to be the cross partial derivatives. Right, this is what we have. So, how are we going to arrange all these things? And we will just take, with respect to this function, let us first calculate all these guys, and then we will know, we will see something interesting here. So, what is, let me do this. So, what is the second derivative of this with respect to x and y? So, now I am going to look at two partial derivatives here and two partial derivatives for this. So, what is it that we are going to get? So, this is going to be the second partial derivative, which is nothing but dou square f by dou x square. So, I am going to look at dou square f by dou x square, and I am going to have dou square f by dou y dou x. And in this case again I have dou square f by dou x dou y and dou square f by dou y square. This is what I am going to look at. So, if I do this, what do I get? Let us check what we get here. So, the second derivative of this is nothing but dou by dou x of dou f by dou x, which is going to give me 6xy squared plus 2y cube, and then I am going to look at dou by dou y of dou f by dou x, dou by dou y of dou f by dou x, and that is going to give me 6x squared y plus 6xy squared. And now I am going to look at dou by dou x of dou f by dou y, which is going to give me 6x squared y plus 6xy squared, and I am going to look at the last one, which is nothing but dou by dou y of dou square f by dou y square, dou y, sorry, dou by dou y of dou f by dou y, which is nothing but 2x cube plus 6x squared y. Right, these are the four partial derivatives that we have. So, what are we going to do? We are going to take this as the, we are going to populate the matrix. We are going to write this way: dou square f by dou x squared, dou square f by dou y squared, dou square f by dou y dou x, dou squared f by dou x dou y. And if you have noticed in the previous example that we did, the cross product terms are the same. Most of the functions which are continuous, the cross product terms will be same, therefore, you are going to have your symmetric property for Hessian. The moment you have a symmetric matrix, all the properties of real symmetric matrix will come into picture. So, this is going to be, I mean, you can populate this. So, what is this Hessian? This matrix is what we call as the Hessian. You can look at multidimensional function of multiple variables. This is going to look like dou square f by dou x1 squared. You are going to have dou squared f by dou x1 dou x2. We have dou squared f by dou x1 dou x3 and so on. And so on. So, I have dou square f by dou x1 dou xn, and the second one I am going to have again dou square f by dou x1 dou x2, dou squared f by dou x2 squared, dou squared f by dou x2 dou x3, and so on, dou squared f by dou x2 dou xn. Similarly, it goes this way. So, you have dou squared f by dou xn dou x1, dou squared f by dou xn dou x2, etc., dou squared f by dou xn squared. So, this is basically the Hessian matrix of a function of n variables, right. And what is that equal to? That is very interesting. Do we see anything interesting here at all? Of course, we do see. What is that? First of all, we had the first column, the first row. If you take, let us just highlight this first row and then see. You take the first row was basically dou f by dou x1, dou f by dou x2, dou f by dou x3, dou f by dou xn, etc. And then you did dou by dou x of dou f by dou x1, dou f by dou x2, dou f by dou x3, dou f by dou xn, and so on, right, with respect to the first one, the gradient with respect to the first one. So, we have, this is nothing but you take the what do you call, the second derivative matrix. So, this is basically the Hessian matrix, which is going to, this is going to be, sorry, this is going to be the Hessian matrix. We will revisit this Hessian matrix when we come to optimization, where this plays a very crucial role, right. So, we have this, it is always symmetric. So, we are going to say Hessian matrix is symmetric. What do we mean by symmetric? We say that dou square f by dou xi dou xj is equal to dou squared f by dou xj dou xi, right. And most, I mean, this property is satisfied by most continuous functions, right. So, most continuous functions satisfy this property. Okay, let us just take a quick example and see like what it is. I will take a quick example. I am going to look at this. This is a function f of x, which is nothing but, let us just take the squared norm of a 3 component vector. I am going to have x1 squared plus x2 squared plus x3 squared. This is what I am going to have. So, let me do this dou f by dou x1, dou f by dou x2, and dou f by dou x3. So, what is dou f by dou x1? I have 2 x1, this is 2 x2, and this is 2 x3. What is dou square f by dou x1 squared? This is 2. Dou squared f by dou x1 dou x2, that is 0, because this function dou f by dou x2 is devoid of x1, then dou by dou x1 of dou f by dou x3, that is also, this dou f by dou x3 is devoid of x1. So, that is going to be 0. Similarly, I am going to do this, since the symmetry condition holds good here, I am going to write this as dou square f by dou x2 dou x1, that is also equal to 0. Then dou square f by dou x2 squared, which is 2, dou by dou x2 of dou f by dou x3, that is going to be 0 here. Then I have dou square f by dou x3 dou x1, which is 0, dou square f by dou x2 dou x3, which is 0, dou square by dou x3 squared, which is basically 2. So, the Hessian matrix is going to be a diagonal matrix, in this case 2 0 0 0 2 0 0 0 2, right. So, this is basically the Hessian matrix that we have. I mean, probably you can even look at multiple functions and stuff. So what we do is, on this note, we will conclude this week's lecture with Hessian. In this week, what we have done is we have looked at the calculus ideas. We started with derivatives. We looked at the higher order derivatives. We looked at the Taylor series expansion, which involves derivatives of function at a particular point. Maclaurin series we saw. Then we looked at properties of we looked at the rules for differentiation, and then we said that, look, this is all fine as far as the function is going to be a function of a single variable, but we do not have that luxury of all the functions being function of single variable. In machine learning especially, you are going to have multiple parameters, especially model parameters. If you do, you are going to have, let us say, multiple parameters. So we wanted to look at what happens when you have a function of multiple variables. How are we going to look at optimizing what is called as a cost function? I mean, what is it that we need to do there? We said we have to take the help of, again, calculus only, but then we said we look at derivatives. And when it came to derivatives, we were not just talking about you're going to have this function of n variables to be varying in all the n directions. So then you said that I will take partial derivatives, keeping all other values, other variables constant. I am going to take the partial derivatives, derivative with respect to one particular variable, that is called as partial derivatives, and we put all the partial derivatives together in a row format, and we call that to be the gradient of the function. And then we said that, look, when I look at gradient, when I stand at a particular point on the surface or probably on a mountain, I may have infinitely many directions, and the slope in these directions are going to vary. Therefore, I want to find out what is the slope of this function or the surface at a particular point in a particular direction, and that is where we got into the idea of directional derivatives. And then we said that, okay, directional derivatives is done, and we found that gradient is the direction of steepest ascent, that means steepest climb, and you have along the level curves the gradient was 0. And then for gradient descent, we said that go in the opposite direction of gradient. Gradient points to the direction of ascent, steepest ascent. If you want to descend, you want to come down, just go in the opposite direction. So the negative of the gradient you take, that is what we said, and that forms the core of your gradient descent algorithm. And then we said, okay, this is not just thing, but then what happens if I have vector valued function? Suppose I want to look at linear transformation, which is going to map n variables to m variables, or m values or m variables. So we had matrix linear transformation. Now what we said is, how are we going to look at the derivatives of these functions? So you said that, okay, stack up all the gradients in the row format. You basically get into the idea of Jacobian. And then we said that, okay, Jacobian is fine. Then we had two layouts, where in which we had the numerator layout and the denominator layout, and we said that you choose one of the layouts for your working and then be consistent with that. And then we said that, okay, I can also look at higher order derivatives, wherein which I am very specific about looking at the second order derivatives. When I looked at second order derivatives, if I just have a function of two variables, I have 4 second order derivatives. 4 second derivatives. What are the 4? There are 2 direct ones, that is dou square by dou x square, dou square by dou y square, but we also have dou square by dou xy and dou square by dou yx, the cross partial derivatives also. And we figured out that if you populate all these second derivatives in a matrix, you end up getting your Hessian matrix, which plays a very vital role as far as optimization is concerned, about which we will see in the next week. So we also took up an example, and we saw that for most of the continuous function, the cross partial derivatives would be equal. Therefore, the Hessian matrix is going to be symmetric matrix. The moment you get a symmetric matrix, our life is very easy, in the sense that you have symmetric matrix, you take all the properties of real symmetric matrices and start working with that. So we did all that in this week, and we are going to follow it up with something more interesting in the next week's lecture. We are going to look at derivatives of matrices, derivatives of matrix operations, derivatives of a lot of interesting stuff we are going to look at. And then we will look at the idea of optimization, in which we look at constrained and unconstrained optimization. We will look at the idea of least squares and PCA from the point of these optimization techniques through matrix calculus, and numerical computation of the parameters which would give you the minimum value, which is basically by the gradient descent algorithm, which would be taken by Gaurav Hegde. And further to that, you of course have lectures by Dr. Ashok Rao on neural networks, perceptron and so on. So, when we come back in the next week, we will look at matrix derivatives. We will be in the week 10 of our lecture, we will be looking at matrix derivatives, constraint and unconstrained optimization and so on. Namaste.